In chemistry, you must learn to deal with incredibly huge numbers, like the number of atoms in a sample, and incredibly small numbers, like the mass of a proton. Chemistry has some great tools to help you do this, like the mole and the AMU. As long as you're familiar with scientific notation, the math behind this isn't too bad. But sometimes it takes a bit to wrap your head around when to use which number. Let's review what each concept is and how to use it to perform calculations. A mole is just a word that describes a particular number. We do this in English all the time. There's 2 in a pair, 12 equals a dozen, score means 20, and gross refers to 144. So what number does the word mole represent? Well, it's a pretty big number. A mole is approximately 602 sextillion. In scientific notation, that's 6.02 times 10 to the 23rd. So we know what number a mole represents. Why do we care? Should we all pick random numbers and give them funny names? Why do moles matter? It turns out that if we have a mole of atoms, we can find out the mass of those atoms from the periodic table of elements. Take a look at the periodic table of elements. They can have slight variations in layout, but for most of them, you'll find 2 numbers in each element's square. One number is always an integer, a whole number. This is called the atomic number. It's the number of protons in that element. We haven't gotten to this material yet in my class, but we will soon. The other number is a decimal. This is called the atomic mass. It tells you the mass that a mole of atoms of that element would have. So how do you do math with moles? Well, when you're confronted with a challenging math problem, try to do a simpler version first. Instead of worrying about moles, let's look at how we'd handle math with the word dozen. How many dogs is equal to 4 dozen dogs? Remember, when we want to convert between units, we multiply our original value by a fraction that is equal to 1. We make a fraction equal to 1 by putting the same value on top as on bottom, just using different names. We know that a dozen is equal to 12. So how do you decide which goes on top and which goes on bottom, the 12 or the dozen? You arrange it so the term you want to get rid of will cancel out, while you keep the new term where you want it to end up. We want to get rid of the dozen and just say it in terms of dogs, so we put 12 on top and 1 dozen on the bottom so that the dozens cancel out. We get 48 dogs. Let's take it one step further. How many legs do 4 dozen dogs have? Start with what you're told, 4 dozen dogs. Your first fraction should change dozens to dogs, so multiply by 12 over 1 dozen. Your second fraction should change dogs to legs. 4 legs equals 1 dog, so multiply by 4 legs over 1 dog. Your dozens and dogs both cancel, so you're left with 4 times 12 times 4 legs, which is 192 legs. Now that you've got the process down, let's try it with moles. What is the mass of 2.5 moles of boron? We start with the 2.5 moles of boron. By looking at the periodic table of elements, we know that 1 mole of boron equals 10.81 grams. So we multiply our 2.5 moles of boron by a fraction equal to 1. Since we want moles to cancel, we put 10.81 grams on top and 1 mole on bottom. After the moles cancel, we get 27.025 grams of boron. Note that that would be 27 with the correct 2 significant figures. Try a different one. How many moles in 0.70 kilograms of carbon? This time you know the mass, but want to determine the number of moles. The periodic table tells us the mass of 1 mole of carbon is 12.01 grams. We start with the 0.70 kilograms of carbon. First, we convert kilograms to grams. You know there's 1,000 grams in a kilogram. Put kilograms in the bottom so it'll cancel, and 1,000 grams on top. Now you want to cancel the grams and end up with moles, so the next fraction will have 1 mole on top and 12.01 grams on bottom. Your answer is 58 grams. Here's one more example. How many atoms in a mole of sulfuric acid? H2SO4 has 7 atoms in it. Technically, 7 moles is a correct answer. But if your teacher asked this, they probably wanted it in scientific notation, not in terms of moles. So take those 7 moles and multiply it just like we did for 12 over a dozen, but this time It's 6.02 times 10 to the 23rd over 1 mole. You'll get 4.21 times 10 to the 24th atoms as your answer. Note that our answer has 3 significant figures, although 7 only has 1 significant figure. That's because 7 is an exact number. It couldn't have been 6.8 atoms per molecule or 7.3 atoms per molecule. That's not how molecules work. It had to be exactly 7. Treat exact numbers like they have infinite zeros after them. So we saw a really big number, the mole. It has a counterpart that's a really small number, the atomic mass unit, or AMU. What's an AMU? Well, it's a little outdated, that's what it is. A lot of times you'll just see U for unified atomic mass unit. The unified version tweaked the value a bit back when my mom was still a middle schooler, so it's been a bit. You'll still see the term AMU a lot though. Most of the time people are using the old term to apply to the new value, but the two values are so close we're not going to worry about which is which at this stage. An AMU is a teeny tiny mass. It's that tiny decimal worth of a gram. In scientific notation, that's 1.66 times 10 to the negative 24th grams. An AMU represents 1/12 the mass of a carbon-12 atom. The carbon-12 name is something that'll make sense once you've covered isotopes. For my class, we're not there yet, but just hold on, we'll get there soon. Here are a few comparisons that might help you to conceptualize what an AMU represents. They're not quite correct. 1/12 of the carbon-12 atom is the only official correct definition. But an AMU is extremely close to being the mass of one proton or the mass of one neutron. Not an electron though, those are super tiny. You also get almost an AMU if you take 1 gram and divide it into a mole of parts. Each part would weigh 1 AMU. One last problem. What's the mass of 100 caffeine molecules? Start by using your periodic table to get all the atomic masses of carbon, hydrogen, nitrogen, and oxygen. Multiply each one by the number of that kind of atoms in each molecule. So we take 100 molecules times 166.1 AMUs per molecule times 1.66 times 10 to the negative 24th grams for each AMU, and times 1 kilogram over 1,000 grams. After everything cancels out, we get our answer of 2.76 times 10 to the negative 25 kilograms for 100 caffeine molecules. Thanks for watching.